A team of physicists just broke time. Not in a sci-fi way with DeLoreans or police boxes, but in their lab at the University of Toronto, they proved that particles of light can experience time running backwards, spending a negative amount of time inside a cloud of atoms. It sounds impossible. Everything takes some amount of time to happen, right? You can't get somewhere before you left or finish a race in negative seconds. But Daniela Angelo and her team just proved you can, at least if you're a quantum particle of light. Their paper, published in September 2024, demonstrates something physicists have speculated about for decades, but never directly measured. Photons can spend negative time exciting atoms as they pass through them. When we measure how long photons spend exciting atoms as they travel through our atomic cloud, we sometimes get a negative answer, reads the research paper. Just let that sink in. They measured something taking less than 0 time to happen. To understand why this is revolutionary, consider what normally happens when light passes through any material. Water, glass, even air. The light slows down slightly, taking a measurable time to travel through. Physicists call this the group delay. It's always been positive because, well, how could it be anything else? But quantum mechanics suggested something stranger might be possible. At the quantum level, where particles can exist in multiple states at once, time might not work quite like we think it does. Proving this required an extraordinary experiment. First, the team had to create perfect conditions using a cloud of rubidium atoms cooled to near absolute zero, around -273 degrees Celsius. At these temperatures, atoms barely move, allowing for incredibly precise measurements. They then sent carefully controlled pulses of laser light through this atomic cloud while measuring exactly how the light interacted with the atoms. Each pulse contained just about 100 photons and lasted mere billionths of a second. The results proved remarkable. When they looked at photons that successfully passed through the atomic cloud without being absorbed, these particles showed clear evidence of having spent negative time exciting the atoms along their path. The measurements revealed photons spending anywhere from -0.82 to 0.54 times the normal interaction time within the atomic cloud. Those negative numbers represent something that seems to defy logic: quantum particles experiencing time in reverse. This isn't just a physics curiosity. The ability to control and measure quantum effects at this level is crucial for developing future technologies. Quantum computers, secure communication systems, and ultra-precise measurement devices all rely on understanding exactly how light and matter interact at the quantum scale. The experiment itself pushed the boundaries of what's possible to measure in a physics lab. The team had to detect changes in light's properties as small as 10 microradians, the equivalent of measuring the width of a human hair from a kilometer away. Achieving this level of precision required averaging measurements over tens of millions of experimental cycles. Their experimental setup reads like a recipe for quantum sorcery. Take one cloud of rubidium atoms, cool until they're nearly motionless. Add precisely controlled laser pulses. Measure the results with mind-boggling accuracy. Repeat millions of times until the quantum secrets reveal themselves. But the real magic happened in the analysis. When looking only at photons that made it through the atomic cloud successfully, the team found something extraordinary. These particles seemed to borrow energy from the atoms before they arrived, then pay it back as they left. A quantum loan that results in negative interaction time. This isn't about sending messages into the past or violating causality. Instead, it reveals something profound about how quantum mechanics actually works. At the quantum level, particles don't follow the same straightforward rules we're used to in our everyday world. The team spent months eliminating every possible source of error that might mimic this effect. They had to account for everything from electronic noise to subtle effects from Earth's magnetic field. Even the natural vibrations of their optical tables had to be considered and controlled. Their success relied heavily on pioneering work with quantum-weak measurement techniques, methods that allow scientists to probe quantum systems while minimizing disruption. These techniques have become increasingly important tools for investigating quantum phenomena that once seemed impossible to study directly. The implications extend far beyond pure physics. Understanding how light interacts with matter at the quantum level is crucial for developing new technologies. Quantum computers, secure communication systems, and ultra-precise measurement devices all rely on controlling these kinds of quantum interactions.